whatever it means.
Thank you. Yeah. Yeah, it's a pleasure to be here to talk about Philippe's work. So the period I'm going to cover is between 2003 and 2012, I believe. This is when I got involved in Philippe's research on the combinatorics of loop models. So I'm going to say a few words about that. But so yes, so I was trying to. So it was a pleasure, kind of reminiscing all these years. These were really exciting years. Well, Philippe wrote like tons of papers on this subject, some of which were with me. It was a very, very exciting times. It was fun, working together was, well, working with Philippe is always a lot of fun, and so it was really nice to. I remember these years, and actually when Jérémy just ended his talk, he was asking, what did Philippe teach me, and I was thinking about that, and I was thinking, well, I think Philippe is an optimist. I'm a really boring, no-nonsense kind of person, like a pessimist, basically, but Philippe is an optimist, so he taught me optimism. Yeah, it was early in my career, and I thought there was no way to solve, all problems are either already solved or unsolvable, and he taught me that we can still solve some nice problems, and we did together, and it was great, and so that was great, and so I want to talk about that. But first, so first I tried to do, I guess, the same thing that the other speakers did, which is to try to find all pictures. And I found it very hard to find pictures from the period of 2003 to 2012. I blame moving to Australia for that. I don't know what happened to all my pictures. So the only pictures I find is really bad, and I apologize for this, but I thought I'd show it anyway. This is him here. This is a workshop we went to together, though it was kind of a nice workshop at the Erwin Schrödinger Institute in Vienna. And sure enough, you can check this is him, and apparently it must be me, I guess. So I don't even know who took the picture. I only have 2 pictures from that workshop, though it was a nice workshop. And by the way, this person in front is Dimash Totenko, but you really can't see it. And to be fair, I only have 2 pictures from this workshop. Oh, that's disappointing. You can't really see. This is the famous Solvay conference, but you can't see, it's too dark. So anyway, we're in good company, with a. So yeah, that's this cafe we went to together near the ESI, which has the picture of this famous Solvay conference picture. So at least we were in good company. But anyway, so really the only nice pictures I have are a little bit later, but they're still relevant because this was a conference in honor of, in memory of Stroganov. And as the name has already been mentioned, our work really originated in some observations by Razumov and Stroganov. So I thought this was appropriate. You can see quite a few familiar faces. In there, I don't know if you can quite see, but Philippe is enjoying the free wine at the conference. It was free wine every meal, and this is most definitely wine he's having. Jean-Bernard in the background has decided that wine is not strong enough for him, and a true way to honor Stroganov's memory would be to drink vodka, so he's merrily shaking his bottle of vodka. And so this is a conference in honor of Stroganov, and that's another one, another picture I found was really nice. We were talking about the smile. You certainly have a great smile on your face on that particular picture. But the thing is, already in 2014, this is kind of beyond what I want to talk about. In fact, Philippe had already moved on. You can't read it either, sorry. The title is something about discrete integrable systems, so he had already moved on to his next subject. So we have to kind of go back in time and go back to the period that is 2003, 2012. So first, let me just show you. This is all the papers on this subject that he wrote. That's a lot of papers. I haven't bothered to count them, but there's a lot. That's right. So the PDF in the title is just Philippe. The other initials, hopefully, I'll say a few words about. And so really, So So also I should say, what is, how did I start working on this? Well, you know the saying, if you can't beat them, join them. So, there was this really strong team in Saclay, and they were doing all this great stuff. Some of it was shown before, so I thought, well, might as well work with them. So I went to Philippe and said we should work on this Razumov-Stroganov conjecture, and with Jean-Bernard also we started working on things related to that. And so. So most of the papers were written in this very short period of time between 2003 and 2007, and there's a few extra in 2012. So I want to just maybe say a few things about, So I'll just briefly flash a few slides on actually what we did together. So there was this original paper with Jean-Bernard and Philippe, which was about bijection. So we were interested in loop models. So the whole story here is just about loop models and their combinatorial properties. So I'll just flash some pictures without telling you exactly the details. But this is a typical loop model. You have edges of a lattice that are either empty or occupied, and you start doing things like drawing continuous lines in between. And we noticed that actually in the case of a particular type of fully packed loop configuration, so a particular choice of model and also a choice of boundary conditions, we could actually find a bijection with plane partitions, which you can think of as lozenge tilings. So this is kind of our first result in this subject. In 2003, we said there is some bijection between some classes of fully packed loops and some classes of lozenge tilings of a hexagon with arbitrary sides of the. And so this was kind of, from my point of view, kind of preliminary work, but it was important because it was a very nice case where we understood everything about these loop models, and we could really understand the combinatorics. And I certainly, and Philippe also went back to this case many times as a kind of nice check of our results. And so this was the very first paper. So then Philippe started working more directly on this Erasmus-Stroganov conjecture, which really describes it in detail, gives an explicit expression for certain loop model data. And in particular, he wrote these two interesting papers, refined conjecture 2. And so that really got us started because we really wanted to prove those results. And so I want to say a word about this paper. So I'll make a selection of a few key results. I'm a bit biased, obviously. Most of these results are the ones that I worked on. Sorry about that, that's obvious bias. But anyway, so here's, for example, one cool result we had in this paper that I just mentioned. So now the game is as follows. You take a half-infinite cylinder, viewed in perspective, and you decorate it with little squares, and you randomly flip a coin, and each time you fill all this cylinder with this pattern or its rotation 90 degrees. Sorry. And so you get something that looks like that. So that's your typical loop model. And the question you ask is of probabilistic nature. You ask, what is the probability that if you look at the boundary points, you start following the loops around, what's the probability that you get this kind of regular pattern where each point k is connected to 2 plus n minus k with some numbering of the external vertices. And so let me just show you in this example, it is the case. You find 1 is connected to 12, 11 is connected to 2, and so on. So it's, of course, one out of many questions you could ask about this model. In particular, there's no particular reason to choose this particular pattern. You could choose other patterns, but this is the one for which the answer is nicest. And so what we proved with Philippe in 2005 is that the probability of such an event is that it's exactly 1 over an integer number, and that integer number happens to be the number of alternating sign matrices. So that's the ASM in the title, and I will give a definition of ASM, not a definition, I'll show you what an ASM looks like in a few slides, but let's just admit that there is a nice explicit formula in terms of factorials, so you get 1, 1 half, 1, 7, 142, in terms of n, which is the number of the size of the cylinder. Now, this is a good occasion for me to also remember that, as I said, we were writing so many papers, it was such a rush all the time that we write the paper, the next day we put it on the archive, we start moving on to the next one. So for example, this particular paper had a different title originally. It was called Proof of the Erasmus-Stroganov Conjecture. Now, for those of you who know the subject, you know that this was only proved much later by Contini and Sportiello, and it's a completely different story. So after we wrote the paper, already put it in the archive, we realized, oh wait, first we didn't prove the Erasmus-Stroganov conjecture, and second, the result we proved was not even due to Erasmus-Stroganov anyway. It was a completely different result. So we decided to modify the title the best we could, so now it became around the Erasmus-Stroganov conjecture, whatever that means, you know. So that was, I guess that's also the fun part, but also sometimes a bit scary part about churning out those papers one by one. And sometimes we'd have to frantically revise the version on the archive because, you know, there are misprints, errors. It was just all chaotic, but it was fun. So anyway, just for the record, there's another variation of this result which I quite like as well. So this one is more interesting. So this time you allow 3 different types of little squares. Either the previous ones where where kind of you have two lines avoiding each other, but you also allow with probability 1/9 that they cross each other, and the other two, let's say, with equal probability. So you play a similar game, but now the pictures look a little bit different because sometimes the lines cross like here, and you ask the exact same question. Right? You ask the exact same question. What is the probability that if you follow the lines? Oh, let me just show you the example. So this is an example which works as well. 1 goes to 12, 2 also goes to 11, even though it crosses twice the other line. Everything works the same. You ask the exact same question. The answer is different, because it's a different model. And again, this is the theorem that we proved, that in this case, it's a ratio of 2 integer numbers. The denominator is some explicit determinant, which has some meaning which I don't want to discuss. But the numerator is kind of interesting. It's kind of already in the realm of commutative algebra or algebraic geometry. It's the degree of a variety. It's the degree of the commuting variety, which is the degree of the pairs of matrices of size n, complex matrices, let's say, that commute with each other. So you think of this as an algebraic variety. You slice it with random hyperplanes until you get a finite number of points. That number of points is this degree. So there's a very nice enumerative geometry meaning to this. So that was another paper. Sorry, now it's going to be really hard to scroll back each time. So I jumped to this paper here. So there's a bit of a connection to algebraic geometry, which I thought was really cool. So then Philippe wrote a whole bunch of papers about open boundaries, like this one. So for each picture on the cylinder, you can do a similar game where now instead of having a cylinder, you have a strip, a finite strip, so finite, semi-infinite rectangle, I guess. And because I was not working fast enough, so he was on the side doing other parallel projects. So there was the one with open boundaries and boundary QKZ, and it was just like, it was crazy. So the next one I want to talk about, I'm not sure actually, so I have to cheat and look. So I wanted to find a few more. In the title, there's also TSS-CPPs. So that's also work of Philippe, which then I kind of joined the team later. So Philippe observed the following: that in the process of looking at those loop models, we consider something called the quantum conditioning homological equation, and the application to loop models was when there was a free parameter in this equation, which is the q of the qkz, and only when q is a cubic root of unity does it have a direct connection to loop models. But in principle, you can take the solution for any q. And then he observed there was this weird connection to another unrelated combinatorial object, which is this totally symmetric self-complementary plane partitions. And so he observed that if you take the sum of all the entries, I'm not going to define, of the solution of the QKZ, which is relevant to the loop model, but you keep Q generic, then you get a weighted sum over TSS-CPPs, where the weighting it's complicated to define. It's supposed to be defined on this picture, so it's something to do with the number of lozenges in some fundamental domain. And tau here is Q plus Q inverse. So there's a very nice and explicit conjecture he had for this kind of generating series of TSS-CPPs. And sure enough, we managed to prove this a few years later. And as I said, if you take Q to be a cubic root of unity, then tau is 1, and you just find the number of TSS-CPPs. So you find another classical result, which is the number of TSS-CPPs is the number of ASMs, which is the one that occurs in loop models. Even though there is no non-bijection between these things, we recovered this classical result. And the final result I want to talk about, so we're still missing the DPPs in the title. And also, I still haven't told you what an ASM is. So the final combinatorial objects that we played with are, so on one hand, ASMs, which already occurred before. So now let me tell you what it is. I'm sure many of you know, but if you don't know what it is, it's an square array of numbers such that if you ignore it's made of zeros, ones, and minus ones in such a way that if you ignore the zeros, then the ones and the minus ones alternate, always starting with a 1 and ending with a 1 in every row, every column. So ones, minus 1, 1, minus 1 on every row, every column. And so it's a very famous combinatorial story that to enumerate such ASMs, and I showed you before the formula. There is an explicit formula in terms of factorials. And then you can consider, and as I said, it's the same formula for the number of TSS-CPPs, but the funny thing is there's yet another object which is in enumeration, which is those descending plane partitions. So again, I'd rather, you can define them using numbers and partitions, but I'd rather think of them as pictures. It's again some kind of tiling model, but a different one. So it's a tiling of a hexagon which is almost regular, but not quite. So it has like size n, n plus 2, n plus 2, n plus 2, and you have a central triangle hole in the middle. And you have cyclic symmetry, 120-degree symmetry. So that means the fundamental region would be, I guess, this region. And so the funny thing is, once again, these are enumerated by the same sequence of ASMs. So so this was known before, but there was one conjecture remaining in this whole literature, a conjecture from I might as well show because I don't remember the year. Yeah, so there was a conjecture from '83 by Mills, Robinson, Rumsey that there was a triple weighted enumeration of ASMs and DPPs which agreed. So in other words, you could put statistics on ASMs and DPPs in such a way that the weighted enumeration would agree. And we actually find even a more generalization of that. And I think it's a pretty cool result because at least on the ASM side, it's very clear what you're doing. So, okay, so first the theorem. Oh yeah, by the way, this is RB. I haven't defined the other co-authors you already knew, Jean-Bernard. So here's, you may notice that eventually we admitted in this very restricted circle people with only 2 letters in their initials. That was an exception we made for, so this is Roger Barron. So yeah, so with Roger and Philippe, we managed to prove a very strong result, which is that if you put a quadruple statistic on ASMs and DPPs, then their enumeration agrees. And so on the ASM side, the statistics are very natural. It's the number of -1s, a generalization of the inversion number of a permutation, because these are generalizations of permutation matrices, and finally the location of the top one and the bottom one, because on the first row and the last row you only have 1, so you can pick its location. So that's so now the game is to find corresponding statistics on the DPP side, and we for 3 of them it was already known, and we found the 4th one, and we managed to prove the accurate enumeration. All right, I'm not going to take more of your time because I think I'm probably already late. So Emmanuel showed us a sequence for Philippe 60th. So here's my sequence. The exercise for the urgency to find which conformal field theory this is the character for. I'll let you think about that. But so congratulations, Philippe, on reaching order 6 of this character. I helpfully included the order 7. So until then, I wish you heaps and heaps of new adventures, as they say in Australia. And thank you.
Okay. Okay, so I'm the last organizer / collaborator this morning, you'll see with relief. So thank you everyone for coming here, and I'm not going to describe everything that Philippe did in the last, since he finished collaborating with Paul Zinn-Justin, but I'll say a few things, and I will not list a bunch of papers. Here are some of Philippe's favorite objects. Maybe this is one way to organize this. And the first one is Chebyshev polynomials, because this is how we always get started. Partial fraction decomposition, Gessel-Vienot, heaps, dimers, hard particles. You've heard these mentioned. Generating functions, continued fractions, all of these. Okay, these are in his tool belt, and he's always pulling them out. And Philippe's hobby is calculating. It's also his love. And Philippe's superpower is also calculating. I'm not saying this in a derogatory way. It's a fantastic ability. And his motto is that formulas speak to him. That's one of his mottos. I know he also, there's a lot of pictures, and there were a lot of pictures in some of the other talks, but they start with formulas. And then his role model is called Stakhanov. For those of you who know. And this is Philippe on vacation in Jenner on Highway 1 in California, calculating. There are seals outside. You can't see them out the window, but he's calculating. Right? Okay, so formulas. So I'll start with the formula. Apologies to everyone. I met Philippe in 2006 in some conference in London where he was describing this work with Paul Zinn-Justin. And I came to visit in 2007, and he told me, "What are you working on?" And I showed him such a formula. It's sort of one in a long line of formulas called a fermionic formula that I needed to prove some identity about. So this is precisely what Philippe does best. So it's some sum, and what you see here are sort of t binomial coefficients, some power of t, and it's a sum over, those of you who know quasi-particle numbers with some selection rules, which I won't detail here. And what this does is it counts with a grading the Hilbert space of some generalized Heisenberg model, and it's such a formula for every Lie algebra and for every collection of representations. And so this is a polynomial, depends on some highest weight for the relevant algebra, and t it counts in the beta integers, basically. So it comes from beta ansatz. And I showed him this formula. I said I need to prove that the selection rules are something. I need to prove a positivity condition for these selection rules on these summation variables. So it's very technical. But this is what Philippe does. Philippe was sitting in I think Père Lachaise, waiting for me to take some French class. And he sends me a text. I solved your formula. It's Chebyshev polynomials. So what do? You form a generating function, you relax the summation rules, and you put in two variables. Here, later on, we discovered we needed two variables which are non-commuting, or mildly non-commuting, so t-commuting. And you have no selection rules, and you start out with such a generating function. And the constant term of this function is constructed to be so that when you evaluate it, when q0 equal to 1, it's the fermionic formula that I showed you on the previous page. But if you look at this formula, you can actually sum it, and it factorizes. It has this beautiful factorized form into a product of, in fact, there are characters, in this case of SL2, finite dimensional representations, but it's some factorized formula, and provided that these Qs satisfy a recursion relation, which is the SL2 quantum Q system. So you get Q of k plus 1 as a function of qk and qk minus 1. And I'll obsess about this formula in a second. But once you have a factorized form, then you can prove anything you want, all the identities you want about the original generating function. I say this not because I want you to notice this particular formula, it's because I want you to notice this last recursion relation, because this is where the Chebyshev polynomials show up. So Chebyshev polynomials, you can define them second kind. U0 is equal to 1, U1 is equal to 1, and UN plus 1 is defined in terms of UN and UN minus 1. And obviously, since it's called a polynomial, it's a polynomial in Y. U1 is Y. Okay? But then you can, again, you can relax the initial data for this recursion relation. And then what you can say is that UN is a Laurent polynomial in X and Y. So this is because it's a mutation in some cluster algebra. We discovered later. Well, you can relax. We can relax. Well, first of all, what you can do is you can renormalize your Chebyshev polynomials, and you can put a plus sign here. This is very important for some reason, mathematical reason. So this becomes your Chebyshev recursion with a plus sign. And then this Rn is not just a Laurent polynomial in the initial data, but it's a Laurent polynomial with positive integer coefficients. And you can relax this some more, make it more complicated, and you could say, okay, suppose these R's q-commute, and you write this recursion relation instead of this recursion relation. Then you still have Laurent positivity. Rn is a Laurent polynomial in R0 and R1 with coefficients which are polynomials in Q with positive coefficients. And finally, this is something Kontsevich taught us. You can make this even more complicated and say, suppose that these R's belong to a completely non-commutative algebra. I don't know anything about them. Then this recursion relation moves to this recursion relation. What you see here is C, which is the commutator, essentially, of Rn plus 1. And this is an equation for completely non-commutative variables. And the Kontsevich conjecture was that Rs is not just Laurent, but it's Laurent in R0 and R1. So words in R0 and R1, the words have coefficients in 0 and 1. Okay, so from Chebyshev, you can go here. This is the most, for rank 2, this is the most complicated you can get. And then I want to go to another word in the title, which is path. So Philippe noticed that all of these things had path solutions. And when you have path partition functions, they lend themselves very well to non-commutative problems, because you can make the weights be non-commutative, and the ordering is determined by the order in which you take your path. So path solution, first of all, there's integrability. This is an integrable recursion, even though it's for non-commuting variables. you have two integrals of motion. The commutant is independent of n, and the Hamiltonian, I call it a Hamiltonian, it's some expression in any two consecutive initial data. It's a Laurent polynomial. It's independent of n. So we call it a conserved quantity. And so the linear, we heard this before several times. Okay, you have an integrable system, you have a linear recursion relation satisfied by these r's, and the coefficients of this linear recursion relations are constant. They're these conserved quantities. You can solve it in terms of paths. And so Rn is essentially a path partition function on a weighted graph. So you start at the red node and you walk on this graph, 2n steps, and that gives you Rn0. So here's a path. Time goes in the right direction, and the weight of this path is y2 square, y1, for example. So you go here, 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 so. Okay. You go here, 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 and here. All right, so path partition functions. And then you move beyond this to generalize to higher rank Chebyshev. I'll just say this very briefly, because it will come back to haunt us on a couple of days from now. So Q systems. So this is the renormalized Q system. For higher rank, for SUN, this is a generalized Chebyshev type equation. So you have A, which has to do with the label of the Dynking diagram. But again, it's a recursion in N, and you can consider it to be discrete recursion relation, discrete evolution. N goes to n plus 1 is a discrete evolution. And RAK is again a Laurent positive polynomial for any valid initial data for this recursion relation. And it has conserved quantities, and the first one is a sum of monomials yi, which I don't list here, Laurent monomials in the initial data. And again, I have a linear recursion relation, and this time the solution is the partition function of paths on this slightly larger graph. Again, these weights can be Q commuting. But again, so if you look at this recursion relation, this is the solution for R1, n, paths of length 2n on this graph. And if you want the solution for RAN, this is another one of his favorite objects, you can look at this relation. It's a de Nano-Jacobi relation. For Wronskian determinants, RAN is a Wronskian determinant in the R1s. And so therefore we have Lindström-Gessel-Vienot theorem. The solution for RAN is a family of A paths on the same graph, which are non-intersecting. So here's an example of such a three such non-intersecting paths. Again, these weights can be Q commuting and so on. This is actually Philippe working in a California parking lot. It doesn't look like a parking lot, but that's what parking lots look like in California. The common denominator of the formulas that I showed you before turned out to be something called cluster algebras, which are objects introduced by Fomin and Zelevinsky in 2000. And you can quantize them. There's a quantization by Bernstein-Zelevinsky based on work with German, Shapiro, and Weinstein, Fork and Goncharov. So just a very random, it's an algebra with generators, and the generators sit on these nodes of this regular n graphs. This is a 3 graph. Okay, and so on these nodes you have these things called cluster variables sitting. In this case, you'll have 3 cluster variables, plus an exchange matrix also sitting at each node. And the generators at each node are related to the generators in the nearby, next door neighbor nodes by something called mutations or exchange relations, and those are precisely the recursion relations that I showed you before. So the Chebyshev recursions or the Q system recursions are precisely mutations of cluster variables. Therefore, the solutions to these equations are A-type cluster variables in some cluster algebra. And the basic properties about cluster algebras you should know are, one, the Laurent property, which was proven in the original work of Fomin and Zelevinsky. Any cluster variable anywhere in this cluster tree is Laurent polynomial in the clusters in any other node in this regular tree. That's the first property. And the second sort of property, conjecture / theorem, is that this Laurent polynomial has positive integer coefficients. So what we're discovering is just a small part of this big field. So Q systems that I showed you before, what I called sort of generalized Chebyshev, they have to do with an exchange matrix, which is, it's a skew-symmetric matrix. If it's a skew-symmetric matrix, you can write it as a quiver, and this quiver will look familiar to a few people in the audience, especially those of them who worked with us on it. So this is the Q system quiver. And so somehow this governs the skew system cluster algebra. So each Q system relation is a mutation in this cluster algebra. So if you can find a past solution, then you have some sort of positivity proof, at least for the cluster variables that we're considering. And so there are Q systems for each affine root systems associated with a similar quiver, and so we have a family of cluster algebras. Okay, and then finally, what we've been doing more recently, so I'm not listing papers, but so here's the quantum Q system. So these variables, they Q commute in this way. So these is the same system, only I put the minus sign here because it's important, and there's a Q to the A on this side, and there's a slightly don't commute if they're nearest neighbors, but that's about it. And this is, again, it's an integrable quantum evolution in discrete time. And the conserved quantities of this system are quantum discrete Toda Hamiltonians, we discovered. And so, and together with the cluster variables, these generate some limit of the spherical double affine Hecke algebra. And in fact, you can find solutions to this equation in terms of Q difference operators. These Q difference operators look like McDonald operators and sort of time translation operators. And this is something that maybe if you listen to Alexander Shapiro's talk on Wednesday, he will tell you a little bit more about. So this is where McDonald theory comes in. So, and then I will not talk about this. I don't know who's talking about T systems, but there is a further generalization of Q systems, which is Q systems of spectral parameter. And this is basically the octahedron recursion relation. If you have 5 points on this diamond, you can get the 6th point by using this recursion relation. So you can view this as an evolution in time variable k now. I don't know if this picture speaks to you. But so this is an infinite rank cluster algebra. And then you can, okay, this is just to give you the next picture. You have any valid initial data for this recursion relation, you have to specify the initial data somewhere. So you pick some initial data surface k of A and J, so it's going to be infinite in general. And if it's sufficiently regular, so you can describe Tijk as some sort of dimer partition function in a region which is a finite slice of this initial data surface, S0. And this is a picture given to me by Philippe's student, Trang Wu. I don't know who's responsible for this picture, but this shows you something about, so this blue thing is an initial data surface. It cuts into this pyramid, and you can ask questions about large k asymptotics, k being the time parameter. And you get Arctic curve phenomena, which I guess we'll hear something about later. Maybe we already heard something about it. For the partition function on this initial data surface, and so on. So talks later this afternoon. So that's all I want to say about this. So happy birthday, Philippe, and in Hebrew we say 220.